Good day. We are Jian Buenaventura, Anjelique Cabarles, and Dennise O, and we will be presenting our research study entitled Generating Evacuation Routes Using Optimization and Simulation Models.
So the study aims for objectives to be accomplished, and we created a framework for each objective where input, process, and output are shown. So the first objective is to assess the current evacuation plan of the digital building in Kumo National Institute of Technology. So to comply with this, we have conducted an assessment of the current escape route in the said building and constructed a network diagram to visually show the direction of occupants toward the exit of the building. This was based on the layout of the floor plan provided by the university. Other numerical data like capacity of rooms, exit stairs, and exit doors was provided as well. Related journals and articles were studied as supporting facts and basis of different methods used in the study. So after the assessment, the problem was then identified, and it was also observed that the building doesn't have a particular routing for occupants in every room as direction guide when emergency occurs. However, the university has a general routing for every floor in the building which only shows the possible direction that occupants can pass by leading to the exit. For the second objective, it is to establish the optimal or shortest route of each room towards the exit doors of the building. So the inputs for this objective are the network diagram showing the layout of the current escape route and the numerical data collected, such as distance measurements and capacity of rooms, exit stairs, and exit doors. For the process, network diagram was created to formulate the network flow programming model. With this model, an optimal route was generated for every room in the building using the Excel solver, considering only the distance. Then transportation model was also formulated, whereas capacity of rooms, exit stairs, and exit doors were already considered as constraints, and it was solved by using Excel solver as well and AIMMS software. These models determine the room assignment for each exit together with the generated escape route floor layouts. Next objective is to determine the shortest egress time in the digital building. So the framework shows that the formulas and constant values from related studies and data from the optimal routes, such as room and exit door capacity, were used to compute the evacuation time for each exit door. Another parameter in computing the evacuation time was the room and exit door dimensions, which specifically needed for the travel time of occupants within an area. Both models obtained different total evacuation time for every exit, and from this, we already identified the shortest evacuation time by comparing the result of the two models. And lastly, the study aims to develop and propose an escape route from each room to the exit door, and policies and procedures for the digital building. So showing the IPO model for this objective, generated optimal route and computed evacuation time were inputs in order to utilize the methods to be used. Time study was conducted by the researchers to determine the travel time and queue time of occupants to escape the building. So with the use of Arena software, we were able to create the model of evacuation route of occupants. Simulation modeling was the method used to compare the computed evacuation time of the generated optimal route with the simulated total evacuation time. By means of comparison, validation of models were considered in this study using statistical tests and sensitivity analysis. Through these methods, we were able to achieve the last objective.
As part of the first objective, the researchers assessed the current evacuation route of the building and observed that it is a 5-story building with a basement. The building has a floor area of approximately 5,629.50 meters squared and 257 rooms in total. The distances of each room towards the exit, as well as their capacities, were both provided by the university. Each floor has 4 exit stairs that directs to where the exit discharge is located, the ground floor or the basement. The ground floor and the basement of the building each has 3 exit doors leading directly outside. The current evacuation plan of the digital building does not have an assigned escape route from each room. It only shows the possible evacuation routes with arrows indicating the direction to the designated exits. Moreover, The exit signs are properly illuminated and are wall mounted above every exit stairway, with an arrow indicating direction to the evacuation route of the building. The university also uses a voice alarm system to alert the building occupants that conducts fire drills once every 3 months. The digital building was chosen for this research for the reason that most people who occupy the building belongs to the electrical and electronics and communication engineering department. Laboratories with hazardous, explosive, and flammable chemicals, as well as electric panels, wiring, and equipment are located in this building, which could most likely be a potential ignition source that makes it more prone to a fire disaster. This table shows the capacity of each type of room as well as its dimensions, whereas this table shows the capacity and dimensions of the exit doors in the digital building. To further show the visual layout of each floor of the digital building, the current escape route of the building was converted to 6 network diagrams that will be shown in the next slides. These figures show all the possible paths that occupants may take towards the exit. Every network diagram consists of nodes which represent different vicinities, which may be the lecture room, laboratory room, faculty room, restroom, audiovisual or seminar room, meeting room, space area, and study area. The exit stairs and exit doors of the said building. Nodes are colored to determine its representation: white for vicinities, green for exit stairs, and yellow for exit doors. The researchers observed that the occupants have no designated assignment of exit in the present escape route. With this, it may cause occupants to be congested and may take a longer time to escape the building. For the upper floors, from second to fifth floor, exit nodes denote as the exit stairs of the building. However, the occupants from the upper floors will lead to the exit nodes of the first floor and the basement, which represent as the available exit doors of the building. The figure shown in the current slide is the current escape route of fifth floor in the digital building. As seen on the figure, diagrams are composed of double-headed arrows which connect one node to another and indicate the path direction where the occupants may possibly go to exit the building during fire disaster. Path direction is based on the present escape route for each floor displayed inside the building. So the next slides are the current escape routes for the other floors of the building. So this one is the current escape route of fourth floor in the digital building. This is the current escape route of third floor in the digital building. This one is the current escape route of second floor in the digital building. This is the current escape route of first floor in the digital building. And lastly, the current escape route of the basement in the digital building.
So here are the tools used for optimization. First was a network diagram. This was used to show the representation of the current escape route of the building and the possible pathways with the use of nodes and arcs. Each pathway was created from each start node to the available exit nodes. Besides, this diagram was utilized to construct mathematical equations in order to establish the linear programming formulation of both models. Next was the network flow programming. This was used specifically to transform the network flow diagram to mathematical equations, whereas the objective function aimed to generate the shortest route of occupants. Based from the network flow formulation, shortest route model was utilized to generate the shortest distance using Microsoft Excel Solver. Then finally, we developed a transportation model to determine the variables that could minimize the total routing distance traveled by the occupants while considering how many of these occupants must be allocated on each exit nodes. So going through the components of a network diagram, there are 3 colored nodes and 2 types of arc. Gray denotes as the start node where occupants will come from. White denotes as the intermediate node where occupants will pass by coming from their current place to the exit. And green stands for the exit node where occupants will proceed to escape the building. So next is the arc, which embodies as the connection between two nodes that represents the flow direction of occupants. However, a dashed arc is also a connection when occupants needed to go to a different floor. So moving on, this slide shows the network flow formulation in order to obtain the shortest distance for each start node to the exit node. Thus, the objective function for this minimization problem was established as minimize the summation Cij times Xij subject to summation of inflow Xij equals summation outflow Xij, where I is the origin node of the arc, J is the destination node, C is the distance between arc Ij, and X is the flow rate of arc Ij, 1 if arc is a positive flow and 0 if otherwise. So the constraint was formulated using the flow conserving node concept, where total inflow is equal to the total outflow, which is shown in the figure. So we will present to you 3 sample formulations from 3 different rooms as start nodes going to one of the available exit nodes. Note that for upper floors, exit stairs are the exit nodes, while for first floor and basement, exit doors are already the exit nodes since there is the location of the exit doors. So the first sample formulation is coming from room 12 going to exit stair 1 located at the 5th floor. So formulation of other rooms on this floor and on upper floors such as 2nd, 3rd, and 4th floor can be seen in the appendix. So next sample formulation is from room 42 going to exit door 47 located at the 1st floor. So this slide shows the last sample formulation, which is coming from room 38 going to exit door 43 located at the basement. Note that formulation for the rest of the rooms on 1st floor and on this floor is attached in the appendix. So to solve all the formulations based from network flow programming as discussed a while ago, shortest route model was developed and Excel solver was used. So following slides show the spreadsheet solution, solver parameters, and result of the 3 sample formulations. In this slide, we will discuss to you how the spreadsheet solution of the first sample works. So first, data were entered in cells A5 to C30 of the spreadsheet. The decision variables in A5 to A30 were indicated whether an arc is on the shortest path or not. 1 if it is, then 0 if not. The meters traveled were calculated by entering equals C5 times D5 in E5 and dragging the formula up to E30. The distance traveled was the length of the arc if it is on the shortest path and 0 if not. The total distance traveled, which is cell E31, was the sum of the arc length on the shortest path, and it represented as the objective cell of the model. The entry in F5 is equals to if F4 is equals to A5, then it is -1. Then if F4 is equals to B5, it is 1, and otherwise 0. And it was copied to the range of F5 to K14. This set of entries indicated whether a node in F4 to W4 was the start of an arc, which is -1, the end of an arc, which is 1, if neither, 0. The entry in F31 was equals sum product of D5 to D30 and F5 to F30, and was dragged up to W31. This entry showed the decision variables 1 or 0 for an arc that is on or not on the shortest path by the type of node -1 or 1 for the origin or destination of an arc, and then determined the sum for each node. Each intermediate node was, at most, the start and end of only an arc or not on the shortest path. Afterwards, Solver tab under Data Analysis was clicked and the interface of the solver parameters will pop up. So it shows the characteristics of an optimization model where target cell, by changing cells, constraints, solving method, and aim of the model will be selected. Target cell is the formulated objective cell, which is E31, by changing cells or decision variable cells, which is D5 to D30, subject to the constraints of variables are binary, D5 to D30 equals bin, and of selected start and end node are equal to the formula of whether a node of an arc is the start, intermediate, or end node. Solving method is simplex LP, and aim of the model is to minimize. So after solving, the solution resulted to a shortest distance of 49.36 meters to reach exit node 1 from start node 12 with a path of 12 to 11, 11 to 10, 10 to 9, 9 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, and 2 to 1. Then same procedure was applied for all the rooms going to its available exits. So the next slide shows the summary of results obtained for room 12 and the escape route based from the room assignment obtained from the result of the solver. Table 1 shows that the shortest path is 12 to 13 with a distance of 5.4 meters. Thus, people who occupy room 12 should utilize exit stair 13 for them to exit the building as soon as an emergency occurs. So after applying the same process for all the start nodes on 5th floor, rooms will be assigned to their respective exit stair, and this shows that most utilized exit stair on 5th floor is exit stair 13 with 299 occupants out of 983. However, only 206 occupants will proceed to exit stair 13 in going out of the building. Then for exit stair 46 and exit stair 30, it will be used by 258 and 220 occupants respectively. So to easily visualize the room assignment per exit stair, we used colored nodes for all the rooms in the generated escape route: red for exit stair 1, orange for exit stair 13, blue for exit stair 46, pink for exit stair 30, and green represents the exit stair itself. So this slide shows the spreadsheet solution and solver parameters for the second sample formulation. So the next slide shows the results obtained from the LP formulations for all the start nodes, including the exit stairs on first floor, where occupants from upper floors will pass by before going to the exit doors of the building. So as observed in the generated escape route, there is a different color representation applied from the previous, since exit doors are already represented as exit nodes, which are yellow, red for exit door 7, pink for exit door 43, purple for exit door 58, blue for exit door 61, and cyan for exit door 69. Third sample spreadsheet solution and solver parameters are shown in this slide, where room 38 is going to exit door 43 located at the basement. So the next slide shows the results obtained from the previous spreadsheet solution. Then, as you can observe, the escape route was created with the same color representation from the first floor, which just added green colored nodes for the exit stairs. Then note that attached also in the appendix is the summary of results of all the rooms obtained from the shortest route model and the generated escape route for second, third, and fourth floor.
As we have already shown you the assignment of the rooms to the exit nodes based on the shortest route that they could travel to, we will now present to you the transportation model that we have formulated, where we could get an optimal solution considering not only the distance of the rooms to the exit nodes, but also considers the number of occupants or evacuees per room and the capacity of the exit stairs and exit doors. Now, for the overall transportation model formulation, the problem is to determine how many occupants should be assigned to each exit stairs or door in order to minimize the total distance that the occupants or evacuees will travel in order to escape the digital building. Therefore, we establish our decision variables as the number of people to be assigned from start node I to exit node J. The objective function represents the total distance for each route, where it should be minimized. So, each term in the objective function reflects the distance traveled by the occupants from its origin to its destination. The first part of the constraints in the linear programming model represents the supply constraints or the number of evacuees at each room of the said floor, while the second part of the constraints represent the demand at each exit or the capacity that the exit nodes could occupy. The following slides show the two kinds of transportation model that we have formulated. This slide shows the transportation model for the fifth floor. As said, There are two types of formulation in this study. First one is this formulation for the second to fifth floors, where we use the exit stairs as the demand nodes. In this slide, we show the objective function which answers to the minimization of the total distance for each route. For example, if there will be 10 occupants assigned from room 2 to exit stairs 1, then the distance 2.55 meters will then be multiplied to the number of evacuees. Therefore, we have a total distance of 25.5 meters. This slide also shows the number of occupants per room constraints, or the supply constraints of per room. Where, for example, let's consider the number of occupants for room number 2 or room 2. This constraint represents the number of occupants transported from room 2 to all 4 exit stairs. The number of occupants transported from room 2 is then limited to 10 people present inside that room. Note that this constraint, as well as all others, is an equation rather than an inequality, because all the occupants present in the building will be needed to meet the total demand or capacity that the exit nodes could occupy at once. This slide then shows the demand or capacity of the exit stairs constraints. We inserted capacity constraints on each exit, even though the behavior of evacuees is to go down continuously, because it is to utilize and limit the people going out of the exit doors, since there's going to be a congestion once the people are not allocated properly and evenly to these exit stairs or doors. Now, the capacity of the exit stairs was obtained from measuring the flight of stairs and its width, where either an average of 4 or 3 people could occupy per step of the stairs itself. With the mentioned properties, the researchers then computed for the capacity of each stairs, which is the ratio of its capacity size per flight to the total capacity size per flight of all stairs, multiplied by the total number of occupants on that floor. Explaining the behavior of the demand or capacity of the exit stairs constraints, as an example, exit stairs 1 could occupy 227 evacuees, which is then the exact number of occupants allocated to that exit stairs from all the rooms on the 5th floor. Therefore, all that can be supplied will then be supplied in order to meet the demand of these exit stairs. This slide then shows the second formulation for the first floor and basement combined, where it used the exit doors as its demand nodes. We combined the rooms of the first floor and basement of the building because all the exit doors are only located on these floors. Therefore, all the occupants of the building will eventually consider going down to either of these floors in order to have access to all the exit doors when congestion appears. Take note that the objective function of this formulation is still the same as the other floors. In this part, it could also be noted that the stairs on the first floor will also be considered as start nodes, since they will contain the number of occupants going down to either the basement or first floor. The demand constraints are then the capacity that the exit doors can occupy. On this slide, we could see the results for the 5th floor transportation model using Microsoft Excel Solver. We constructed the cost table first, which then obtains the constraints of the formulation, and then the solver table where the Excel solver will input its answers given the parameters on the figure. Take note that we altered the initial solver table since the values given there are not equal to the demand constraints, which should be done so as we have opted for the balanced transportation model. This slide shows the tabulated assignment of the rooms to the exit stairs and the assignment diagram for 5th floor. Exit stairs 1 is represented by color red, exit stairs 13 by color orange, exit stairs 46 by color blue, and exit stairs 30 by color pink. This slide shows a tabulated assignment of the rooms to the exit stairs and the assignment diagram for 4th floor. Please take note that even though the label for the exit stairs per floor is different, it is still the same flight of stairs from the 5th floor to the basement of the building. This slide shows the tabulated assignment of the rooms to the exit stairs and the assignment diagram for 3rd floor. This slide then shows the tabulated assignment of the rooms to the exit stairs and the assignment diagram for second floor. As the Excel solver couldn't accommodate all 504 variables of the transportation model for the first floor and basement combined, we then used another software called AIMS or AIMMS or acronym for Advanced Interactive Multidimensional Modeling System. Seen on the slide are both the AIMS interface and the declarations used in order to run the model, where we mainly followed the process of using the AIMS software in portfolio selection. As seen on the table, for the objective function, we coded its coefficients manually into AIMS logic, but we read all the constraints from the Excel table as it was too many to code, which will then be seen on the next slide. This is the Excel data read by AIMS software. The first picture shows the extraction of the Excel file which was synced to be read by AIMMS, and the second picture shows the declaration of our mathematical program by naming the portfolio as quote-unquote mean_data. The slide shows the solution page of AIMMS as to which we could see the results of the problem. We tabulated these results, which could also be seen on this slide. This is the diagram for the generated evacuation route based on distance and capacity for first floor and basement combined. We colored the nodes on the figure to easily distinguish the exit doors designated for each rooms. Red for exit door 7, orange for exit door 37, pink to exit door 43, purple for exit door 58, blue for exit door 61, and cyan for exit door 69. The occupants of the stairs on the first floor are assigned to different exit doors due to its large number, which was obtained from the evacuees coming from the 5th to 2nd floors. As we considered the exit stairs assigned to each room per floor, we then created a floor capacity allocation in order to assign which exit door thus the occupants of each room should proceed to after going down the stairs assigned for them. For example, exit stairs 44 and 56 are the stairs that can produce occupants that may go to exit door 7, which summates to 447 evacuees. Now, in order to exhaust the utilization of these stairs, we allocated the rooms on the 5th floor that will go down on both exit stairs 44 and 56 and subtracted to the total capacity of exit door 7 to see how much more occupants are needed from the rest of the floors in order to consume the remaining capacity on the allocation row. The tables shown on this slide are then the assignment of all the rooms from 2nd to 5th floor to the designated exit doors.
To determine the evacuation time of the building, the researchers calculated for the total evacuation time for both the analytical and simulation model. This is for the analytical one. The computation of the evacuation time was used for the optimal escape route of each room towards the exit, considering both the distances and capacity obtained from the transportation and shortest route model. Along with this, the evacuation time calculated was utilized for the verification and validation of the model, in which the evacuation time obtained from this was compared to the evacuation time obtained from the simulation model. So what is the evacuation time? It is the time it takes for the evacuees to leave the hazard region and transfer to the safe zone. It is composed of two elements, the pre-evacuation time and the movement time. The formulas used for the computation for the evacuation time are based from the study of Purser. And according to him, the total evacuation time is the sum of the pre-evacuation time and the movement time. All of the exit doors in the building are taken into consideration in solving for the total evacuation time. It is acquired by initially getting the pre-evacuation time of each exit door and adding it to its movement time. The pre-evacuation time is the time taken by the evacuees to be aware of the situation and start to evacuate. Prior to that, the pre-evacuation time has a component which is the pre-movement time. It is where the width of the door, the flow of occupants, and dimensions of the rooms are considered. So this was calculated first to get the pre-evacuation time. The pre-movement time of each type of room was considered since it varies and has different dimensions. The sample computation which will be shown in this presentation is the pre-movement time of the lecture room, pre-evacuation time, and movement time of the exit door that took the longest time. The researchers also provided the computation for other room types and exit doors and can be seen in the appendix. In solving for the pre-movement time, the researchers considered all 6 types of rooms. Since what I've said earlier, all types of rooms must be taken into account as it varies and would affect the results. So the effective width was calculated first as it is the measurement of the door which is the way out of the room. The formula is effective width equals width of the door minus 2 times boundary layer. The boundary layer is referred to as the small distance the evacuees occupy in the egress segment. The boundary layer used for the effective width is constant for all room types and is referred from the constants based from the study of Purser. So, as seen in the computation, the boundary layer of the door, which is 0.15, was multiplied by 2 and subtracted by the width of the door, which is 0.92 meters. So, for the pre-movement time, of the lecture room, the effective width obtained is 0.62 meters. Next, after passing through the door, the movement speed is calculated, or the speed of an evacuee to reach from one place to another. The traveling speed of an evacuee depends on the occupant density, which is defined as the number of people per floor area. In common with the effective width, the values used for this formula are also the constants seen from the study of Purser. The constant value of A, which is 0.266 meters squared per person, was subtracted from K, which is 1.40 meters per second, and was multiplied by the density to get the movement speed. The movement speed we got is 1.158 meters per second. Then, the specific flow or the flow of evacuees passing through a specific exit element, which could be a stair, corridor, or door, is calculated by multiplying the movement speed by the density. So for here, we got 0.753 persons per second meter. Then after calculating for the specific flow, the calculated flow will be obtained by multiplying the specific flow to the effective width. So the calculated width obtained is 0.467 persons per second. Now, as the evacuees make their way out of the room and move towards the hallway, the travel time and queuing time are taken into account to calculate for the total pre-movement time, which is the time it takes for them to respond and start evacuating. So, to get the queuing time or the amount of time the number of people n spent waiting to pass through the small n or the number of exit element, the capacity of each room was considered. So, the capital N, which is 50 in this case, is divided by the number of exit elements, the small letter n, which is 1 for all room types. The total value was then divided by the calculated flow. So for the queuing time, we got 107.147 seconds. Now, as for the travel time, it was calculated by getting the L travel, which is the sum of the length and the width of each type of room. So for the lecture room, it is 21.5 meters. Then it is divided by the movement speed, which is 1.158 meters per second. So the travel time obtained for this one is 18.567 seconds. Then, by adding the queuing time and the travel time, the movement time for the pre-movement time was obtained. So, from here, the travel time is 18.567 seconds, and the queuing time is 107.147 seconds. Adding them together, we get 125.714 seconds as the movement time of the pre-movement time of the lecture room. So along with this, an additional 60 seconds was added to the total pre-movement time of each room for the reason that the university uses a standard voice alarm system. So for here, as we can see, we got a total of 185.714 seconds for the pre-movement time of the lecture room. The pre-evacuation time of all exit doors for both models was calculated to obtain the evacuation time. The pre-evacuation time of exit door 58 is shown on the table. To solve, the pre-movement time of each type of room was multiplied by the number of rooms of each type found on the said exit. Then, the sum of the pre-evacuation times calculated per type of room, which is 10,708.4693, was divided by the total number of rooms, which is 103. Therefore, the total pre-evacuation time of exit 58 resulted to 103.9657 seconds. It is a must to calculate for the pre-evacuation time, given the reason that the capacities and dimensions of the rooms varies and would affect the result of the total evacuation time of the building. After this, the movement time was obtained by applying the same formulas used in the acquisition of the pre-movement time. However, in this particular case, the exit doors leading the evacuees directly outside were taken into consideration, given that the time covered for the movement time is from the moment they start to evacuate, which is the pre-movement time, down to the time they are deemed safe. So on a par with the types of rooms in the building, the capacity and size of the doors varies. Also, the effective width was affected since the width used in the formula depends on the type of exit door. So the movement time for both models were calculated, and the value obtained from the shortest route is 2,345.833 seconds, whereas for the transportation it is 1,577.317 seconds. So to get the total evacuation time, the pre-evacuation time calculated previously was added to the movement time of each exit door. So the evacuation time obtained from the shortest route is 2,446.4350 seconds, while for the transportation, it is 1,681.2830 seconds. As mentioned earlier, the computations shown in this presentation for both models are the ones that took the longest time as base from the computation. So it is exit 69 for the shortest route and exit 58 for the transportation model. Also, as observed from the evacuation times acquired, the evacuation time obtained from the shortest route model took longer as compared to the one from the transportation model. Therefore, the researchers utilized the evacuation time from the transportation model, where both the distance and capacity are considered. The tables show the evacuation times obtained from both models, and based from the calculated evacuation time shown, the longest time it took the occupants to evacuate in the transportation model were coming from exit 58, which is 1,681.2830 seconds. They considered this as the total evacuation time, as it would be the time all evacuees are deemed safe and are out of the building. So as part of the components in getting the total evacuation time in the simulation model, the researchers also conducted a time study to obtain the time it takes to depart from each room to a designated exit for the reason that the arena software only accepts time-based data. So the path followed by them was based from the optimal routes obtained from the transportation model, since the capacity is taken into consideration and acquired a lesser evacuation time compared to the one from the shortest route. They used smartphones to record the time, performed a total of 5 trials for each room, and identified the mean and the standard deviation to determine how spread out the data set is using the input analyzer in the Arena software, given that it has a fit all option, which finds the best fit to the data. So, as observed from the standard deviation obtained from the input analyzer, the values obtained are not greater than 2, which makes it acceptable and near the true value. The table shows the recorded time per trial as well as the mean and standard deviation computed for each room towards the exit door of a part of the fifth floor. The time study recorded for the other floors will be seen in Appendix J. As previously mentioned, the researchers used the input analyzer in the Arena software to obtain the mean and standard deviation of the performed trials and to determine the type of distribution that best fits the set of data. First, the data gathered from the trials performed in the time study were entered in the notepad as shown in the figure. The sample shown was the recorded data from the trials performed in room 203. The file was then saved as the room number, and DST was used as the file extension for it to be compatible with the input analyzer. Then from the Arena software, the input analyzer was launched from the Tools section. From the File menu, New was selected, and then from the Text menu, File, and then Data File, and then Use Existing was selected. The dataset saved from the notepad was opened in the launcher. As shown in the figure, and upon loading the file, a histogram of the data as well as its data summary, which shows the mean and standard deviation of the room, was displayed. However, for this instance, the researchers selected the Fit All option as shown in the figure on the left. This option is to determine the type of distribution that best fits the data, since the input analyzer automatically selects the distribution, plots the fitted function to the dataset on the existing histogram, as well as adds information regarding the selected distribution shown in the figure on the right. Therefore, for this room, the type of distribution selected by the analyzer was beta. That being said, it has been observed that there are various types of distributions in the launcher in which the dataset could be fitted. The list shows the types of distribution used by the researchers: beta, empirical, Erlang, exponential, gamma, normal, triangular, uniform, Weibull, and log normal. The researchers performed the procedure for each room, and the type of distribution that fits best for the dataset collected per room was determined. The given expression was then entered in the Arena software and was used as an element for determining the evacuation time in the simulation model. Now, to completely obtain the evacuation time in the simulation model, the time spent by the evacuees waiting before they could exit the building was recorded as shown in the table. The mean obtained from the 5 trials performed was used in the queuing theory equation as the service rate, and the values acquired from the computation was entered as the queuing time in the simulation model. With all the elements needed, the evacuation time acquired from the simulation model was compared to the one from the analytical model for the verification and validation. So as what I've said earlier, the waiting time in queue was computed to complete the elements needed for the simulation model, and again was achieved using the queuing theory equations. So the queuing time of each exit door was computed and was entered in the simulation model as an element in computing for the total evacuation time. The sample which will be shown in the presentation is for exit door 58. First, the service rate was computed. The means from the time study performed for the waiting time in queue was used to obtain the service rate in the equation. So for the computation of the service rate, the mean from the time study for the queuing time was divided by 1. So for this, we got 0.1806. So as for the arrival rate, the calculated flow from the evacuation computation was used. Now with all the components needed for the equation, the values obtained was used for the computation of the waiting time in queue. So as seen, the formula used is n over the arrival rate minus 1 over service rate. So it is 12 over 1.5808 minus 1 over 0.1806. So for the waiting time in queue of exit door 58, we obtained a value of 2.0540 seconds. So the values obtained from the waiting time in queue was entered in the simulation model to get the total evacuation time of the building. So this shows the waiting time in queue of all exit doors in the digital building. So it shows the type of exit door, the capacity of the exit door, and the waiting time in queue obtained.
On this slide shows the tools used for simulation and validation of models. First is the simulation through Arena. It is the modeling of real-life processes through the means of structuring it into smaller or computer representations, reproducing worldly scenarios to see the results on the laws and rules formed by mankind or any businesses. Second is the statistical test or t-test. It was used in order to show the validation of the value from the computed evacuation time and the values from the simulation. Lastly is the sensitivity analysis. The researchers or we use the sensitivity analysis to determine if the constraints of the model have an effect to the results that it produced. The researchers defined simulation as their validation of the analyzation model or computational model. The simulation model was then constructed with a time study discussed from section time study, and the results obtained through it was used to prove that the analytical model could secure the evacuees' escape in the digital building faster than the current evacuation plan. Arena is a simulation software created to address the effects and impacts of changes that the user anticipates on the created system or in the current process. Since we are using time as data, the researchers focus on the discrete event modeling in Arena, as this kind of simulation anticipates change in distinct point of time. The slide shows the process flowchart where we based our simulation model on. It starts with the alarm detecting the fire smoke, then it will signal the occupants of the building as they were alarmed, they will then leave their rooms and enter the system, which will be modeled on Arena. As they leave the rooms, they will then utilize the hallway before escaping the digital building through the exit doors. With this flowchart, we then distinguished the pieces of the simulation to be used, which are the following: entities, resources, and queues. These pieces are the key players and data in which the process will then use when the model started running. Entities are considered as the players of the model, and they are considered as the evacuees in this study. Resources are the hallways being utilized by the evacuees. And take note that the simulation starts when the evacuees enter the system, or leave their rooms for that matter. Therefore, they are located already on the first floor and or the basement hallway. And with this, we considered using only one quantity of hallway as a resource. Queues were considered as there will be utilization of the resource hallway, which means that there will be waiting time per entity for that matter. We could see in this slide the model for Exit 58 and the modules used for it. These modules are the Create module, Route to Station module, Process module, and Dispose module. The Create module is referred as the arrival of the parts to the system. We use the Create as the rooms of the building where the time intervals were established along with the total number of occupants per room. For the time between arrivals data or parameters, we chose the expression option to declare the distribution obtained from the input analyzer fitted for the room that was being analyzed. For example, Create Module 1 was named as Room B119, and based on its max arrivals, it has 30 evacuees in total. Therefore, it is a lecture room. In terms of transferring the entities from the rooms to its exit doors, the researchers used the route and station modules as the representation of the evacuees, taking the allocated route assigned to them. With the same behavior as the Create module, the researchers used the time study from Chapter 3 Time Study or the Time Study discussion to assign the travel time of the evacuees from their rooms to the exit, which then explains the different distribution expression on each route. The station was assigned to each route to show that the entity is already transferred from their rooms to the exit. And the station is not required to need a physical attribute in the real world, much alone in the system, as it could be solely based on the logic of time incurred in transferring the entities in another module. As the entities traveled already from their rooms to the exit, we then included a process in the system in which the entities will have a queue before they could go out of the exit door, or in this matter the dispose module. We used the hallway as the resource where the delay would be seen because in here, congestions could already happen since the occupiers were simultaneously moving to the exit door. From the values computed as queuing time or waiting delay for each exit from the previous discussions, we could see them being used on the delay type parameter as a waiting delay or them being allocated as wait delay. After processing the delay on the evacuees, they will then be released onto the dispose module where they will be treated like they already escaped the building. The dispose module shows the exit of the entities from the system and records the time where the system has completed its whole run. We then set up the run parameters of the system where the number of replications should be 10 and all the base time units should be as seconds. This slide also shows a sample of the obtained Simon output report from Arena simulation. After disposing all the entities that the Create module produced, the system will stop the running time and will compute for the total time that all the entities have exited the system. The table shows the summary of record of all the total time that the exit modules completed for each replication, also the mean of these replications. We made 10 replications for each exit door in order to implicate the validity of the results, and as seen on the table, it has a standard deviation value of 0.28, which shows or tells us that all replication results are congested to each other and that no matter how many runs the system will have, it will still produce the same range of results. Therefore, 10 replications will suffice for the results of this simulation. We conducted a one-sample t-test to present the validation between the obtained from the computation value and the simulated values. We used one sample t-test since we are comparing 10 values from simulation to a single value from the evacuation time computation. Before proceeding to the construction of the t-table, we then assigned the null and an alternative hypothesis needed to verify the values. The null hypothesis says that there is no significant difference between the simulated result and the computed result. On the other hand, the alternate hypothesis says that there is a significant difference between the simulated result and the computed value. Following the steps in conducting the one-sample t-test, which could also be seen on the table, we then compare the t-value to the t-critical value. T-value is lesser than t-critical, therefore accepted the null hypothesis, which proceeds to conclude that these simulated values have no significant difference from the computed value of the evacuation time. Conducting the one-sample t-test to all exit models, the table shows that the simulated values and the computed values obtained from all the exits have no significant difference from each other, and that the values are of the same range due to the obtained percent error. This validates the computed values from the linear programming model and that the assignment of rooms to be available exit doors of the digital building can then be used as the evacuation plan when a fire disaster happens. In this study, we used the sensitivity analysis to determine if the constraints of the model have an effect to the results that it produced. It was also used to predict case-to-case basis regarding the evacuation, forecasting their increase and decrease in the time when there are changes in the variables used. For case 1, we considered a 50% decrease on the room capacities in the digital building, where we alter the maximum arrivals out of the rooms in the create module in the arena model as seen on the figure on the slide here. The table shows the summary of results for all the exit models. We discerned that the room capacity affect the total evacuation time relatively with an approximate decrease of 47% to 50%, which is directly proportional to the case of decreasing the room capacities to 50%. The researchers also included a case where delay is longer when various human behaviors are exhibited by the occupants. As presented in the study of Shiba, a delay with human behavior takes up approximately 28% of the total evacuation time. It was then conferred that there's an increase of 6% delay compared to the initial as to represent the observed human constraints. Therefore, the researchers added these human constraint delays to the process of the system as seen on the figure on this slide. The table in this slide shows the summary of results for all the exit modules for case 2. The total evacuation time obtained from altering the delay values show an approximate increase of 3% to the proposed simulated value. We observed that as we increase the movement delay, the total evacuation time also increases, which then shows that when we include human behavior on the time input, the effect on the total evacuation time is pessimistic and do cause further bottleneck in the process flow of the evacuation model. As all the constraints and results had been verified and validated, we proposed to use the evacuation routes generated from the linear programming model. This slide shows the assignment of each room of the 5th floor to its assigned exit door. Please note that these rooms should strictly take their assigned exit stairs for them to reach the lower floors and to their assigned exit doors. This slide shows the assignment of each room of the 4th floor to its assigned exit door. This slide then shows the assignment of each room of the 3rd floor to its assigned exit doors. This slide shows the assignment of each room of the 2nd floor to its assigned exit door. This slide shows the assignment of each room of the 1st floor and basement to its assigned exit door.
So shown is the sample for the proposed escape route of 5th floor. So for this one, the evacuee is currently located in room 538. It shows the evacuation route to their assigned exit stairs in the floor. Now on to the next slide. It shows the proposed escape route from the 5th floor to the basement, coming from the exit stairs. So from the exit stairs, it shows the evacuation route towards their assigned exit door or the way out of the building. So the same goes for the other floors. So this one is the sample proposed escape route for the 4th floor, then the 4th floor to the 1st floor, and then this one is the 3rd floor, then the 3rd floor to the 1st floor. Then next is the proposed escape route of 2nd floor, and then the 2nd floor to the basement. Then the proposed escape route for the 1st floor, and lastly, the proposed escape route for the basement. So policies and procedures were also made, as shown in the figure, to serve as guidelines for an orderly evacuation and overall ensure the safety of the teaching and non-teaching personnel, students, and visitors of Kuma National Institute of Technology in case of an emergency. So in conclusion, for Objective 1, which is to assess the current evacuation plan of the digital building in Kumo National Institute of Technology. The researchers were able to evaluate the current evacuation plan of the building and discovered that the building's current plan does not have an assigned escape route from each room. It only displays the possible evacuation routes, with arrows indicating the direction to the designated exits. Nevertheless, the exit signs are properly illuminated and are wall mounted above every exit stairway, with an arrow indicating the direction to the evacuation route of the building. Also, the university uses a voice alarm system to alert the evacuees and conducts fire drills every 3 months. As the researchers assessed the current evacuation route, issues and problems were identified. Due to the fact that the building is occupied by students from Electrical and Electronics and Communication Engineering Department, laboratories with hazardous, explosive, and flammable chemicals, as well as electrical panels, wiring, and equipment are located in the building. With this information, and as what is stated by the National Research Council Committee, the researchers discovered that these materials could most likely be a potential source of ignition, which makes the building prone to a fire disaster.
So as a conclusion for Objective 2, there were two main methods used in order to establish the shortest route for each room towards the exit of the building. These were shortest route model and transportation model. So in constructing network diagrams and formulating LP equations, two optimal solutions were generated based from these two models, using Excel Solver and AIMMS software. Hence, all the rooms in the building were already assigned to its respective exit, where occupants may take the route based on either of the two optimal routes in order to escape the building during emergencies.
So to summarize the findings for the third objective, which is to determine the shortest egress time in the digital building, the researchers determined the shortest evacuation time by utilizing the both shortest route and transportation models as reference. They discovered that the total evacuation time of a building is comprised of the pre-movement time and movement time as stated in the study of Purser. Also, the evacuation time was calculated using the formulas from his study. The pre-movement time was calculated first, in which the 6 types of room were taken into account as it varies. Along with this, an additional 60 seconds was added to the total pre-movement time computed for each room, for the reason that the university uses a standard voice alarm system. From there, the pre-evacuation time was calculated and is added to the movement time to get the total evacuation time of the building. Based from the results, the evacuation time obtained from the transportation model covered a shorter amount as compared to the shortest route model. The longest evacuation time taken by the evacuees in the transportation model was 1,681.2830 seconds and were coming from exit 58. The researchers considered this as the total evacuation time, as it would be the time all evacuees are deemed safe and out of the building. Furthermore, the evacuation time obtained from the computation served as an element for comparison for the verification and validation.
Objective 4. The researchers, or we, were able to create a proposed escape routes from each room to exit door for the digital building in Kumo National Institute of Technology. The assignment of exits in the escape routes were based from the transportation model, as the distance and capacity were taken into consideration. These assignment of rooms to each exit doors were also simulated through the usage of the Arena software. And as we have gotten the results from 10 replications from each exit model, we then validate or test the significance, or if there's a significant difference between the simulated values to the computed value of the evacuation time. And as we conducted already the statistical analysis for this study or for these results, we then conclude that there is no significant difference between the values and that these assignment of rooms should be used or can be used as the evacuation plan of Kumo National Institute of Technology during fire disasters.
And that's it for our presentation. Thank you for watching.